In section 5 of chapter 4, we are again going to be going over another factoring technique. It's kind of like air quotes factoring technique. It is a factoring technique. It is used to solve quadratics, but it's also used to do something that we did previously that I'm going to go over first. Remember back in the day when we were graphing a bunch of different parent functions, and one of the ones I gave you were quadratics, and you described it as moving left or right, up or down, stretched, compressed, all those shenanigans. You might look back and go like, well, I mean, I know they're quadratics. I know they're written like this. I know they're going to make parabolas. I know they're x to the second power type of equations. But the big gap for you is if I just gave you a generic quadratic, like 2x squared plus 5x minus 3, none of y'all know how to get it into that form. And yet when we were graphing, they all came in that form. So there's kind of a gap in our understanding right now. There's a format that we know how to graph. There's the format that quadratics come in. But we don't know how to get from one to the other necessarily. And that's what this lesson is designed for in part. Namely, we're going to use this technique to solve these quadratics. However, I want to first showcase where we used it in the past. So in these problems, the red one would move left 1 down 7. We'd go left 1 down 7, which is right here. You make the pattern for quadratics, which would look something like this. And you could graph it. And in this chapter, we've been solving quadratics to find where they intersect the x-axis. So we're kind of seeing some overlap between the two concepts. The blue one saying we move right 4, up 5. 1, 2, 3, 4, 5. And then we would flip it vertically because of the negative in front of the 1/2, and we compress it vertically by 1/2, so it looks something like this. And again, what we're doing today is not necessarily focusing on the graphing component. We've already done that to a large degree. We're going to be focusing on finding the x-intercepts. The technique I'm about to show you, unlike all the other techniques I've shown you thus far, the nice thing about this technique is it never misses. It always works, every single time. With that said, in mathematics, generally when we have a formula, a technique, an approach to a math problem that always works, the downside is usually when it works, it's either computationally difficult, which is what the next lesson's on, or in this case, you're going to get some ugly answers a lot of the time because it is designed for those ugly problems. So just be aware of that fact. All right, here's the technique. The technique is called completing the square. And just like all the other naming conventions we've used in this chapter, the name has a connection to how we do the technique. The fact that we've been doing factoring using the area model was all to lead us to this point. I know there are faster ways of factoring than the area model. However, this technique is conceptually and mathematically challenging, so I've been designing this chapter, I've been designing us using the area model to factor just so we're ready for this. In most Algebra 2 classes, this is the lesson that tends to make students struggle. That's why I want to go slow, and that's why I've been building our conceptual understanding of area models so that we can do this. All right, so for this problem, I'm just going to get it into that graphing form we just got done doing. I'll show you how to solve with it in the next and last slide. So here's how we do this. We're not going to use an area model as you're used to. We're going to use a different area model, like this. It is missing the bottom right portion. It's an incomplete area model. Additionally, I'm going to make one more specification. This area model we are about to make has to be a square, which kind of makes sense. If our goal is to get something that is going to be squared, we need something that when we draw a shape for it is going to be a square. So what that tells us is the length and the width must be equal to each other. So we're going to put the x squared in this box up here in the top left, just as normal. And if it's a square, that means this needs to be x, this needs to be x. So far, so good. Now here's the nice thing about this technique. Typically, finding what goes in these two boxes is annoying because you have to find all the possible numbers that can combine to get us that negative 8x. If this is a square, both those boxes have to be the same. So all we need to do to the middle term is just cut it in half. Which means I need a -4 and a -4. Now here's where things don't really compute all that well, because that means the part of my area model, if I wanted to make it a square that is missing, is a +16. We don't have a +16, we have a +10. So here's what we are going to do. We're going to take that 10, and we're going to kind of like move it off to the side. We're going to kind of ignore it, just for now, all right? And what we're going to do is, we're just going to add that number that we needed. Now I know some of you might be going like, you can't just add a number into an equation. You can if you also do this. As long as I add and subtract the same number in an equation, I'm not doing anything. If I have a scale and I add 5 pounds to one side and then also take 5 pounds off that same side, it's still in balance. And what we're going to do is with these 3 terms, it creates this area model. Because I completed, by throwing in this piece, I completed a perfect square. This, if you factored it, would turn into x minus 4 times x minus 4, which is x minus 4 quantity squared. And then that stuff that I left on the outside, the +10 and the -16, when you combine those together, you'd get -6. Here's our graphing form of that quadratic. In these next 2 problems, I'm still going to use completing the square. Except now, I'm going to use it as a process to solve equations, to find the x-intercepts, to find the roots of these quadratics. So problem number 1, I have y plus 7 equals 4x squared minus 12x. If I'm asking to solve for x, if I'm trying to find the x-intercepts, the first step is always the same. Turn the y values into 0. So we try to find the x-intercepts, where they hit on the x-axis. All coordinates on the x-axis have one thing in common. They haven't gone up or down. Their y value is 0. So if you're trying to find them, set y equal to 0. Second, we typically like having the quadratic equal to 0. Remember all of our factoring techniques? We like it equal to 0. So I'm going to subtract the 7 to the other side as well. That way this will turn into 0 equals 4x squared minus 12x. And now I'm actually going to leave a little space because I know I'm eventually going to need to figure out a number I'm going to put right here. I'm going to have to add a number right there so it can factor into a perfect square. And I'm going to have to subtract that same value. I don't know what they are right now, but I know I'm eventually going to have to get those values. All right, so I just focus on these things. I'm going to make an area model for it, an incomplete area model. It's missing the bottom right portion. Our job is to complete that square. The 4x squared goes in the top left box. We can do that because 4 is a perfect square. 2x and 2x. These 2 boxes have to combine together to get me that -12x. Just cut that in half. It needs to be -6x, -6x. Now, our initial instinct is to write -6 and -6, and that would be wrong. Because -6 times 2 is not -6. You have to be more careful. We have to ask ourselves, what times 2 is equal to -6? The answer is -3. -3 times -3 is the missing piece, +9. So we're going to add 9 here and subtract 9 there. So those first 3 pieces, including the black 9 that I just wrote, would factor into 2x minus 3 times 2x minus 3, which is 2x minus 3 quantity squared. And then those 2 parts on the outside, the -7 and the -9, those combine to get me -16, and that's still equal to 0. So I just went through completing the square. The rest of this is just a straightforward algebraic process. My goal is to solve for x. So let's just get it by itself. I'm going to add the 16 to the other side. This and this eliminate. You're left with 16 equals 2x minus 3 quantity squared. Give myself a little bit more space. Square root both sides. Square root cancels the second power. Then I got the square root of 16 is 4 is equal to 2x minus 3. We add the 3 to the other side and then divide by 2. Oops, why did I do that? Add 3. Then we're also going to divide everything by 2, divide everything by 2. The mistake I made, and that's why I actually had to stop because I couldn't go any further without actually having to erase a bunch of stuff. Whenever you get rid of a second power by square rooting, remember there are two possible answers, a positive and a negative variant. You need to put a plus or minus. I really like hammering that in because it is the easiest mistake to make and it will cost you points on the test. For getting a negative here and there, I can forgive that. For getting a plus or minus, that tells me you don't necessarily understand the concept in its fullness. Make sure you put the plus or minus, because that changes things. Because now it's not 4 equals 2x minus 3. It is going to be plus or minus 4, and that's different. For those that do not know, plus or minus is mathematically, it technically means there's two equations right there. The first equation is 4 equals 2x minus 3. And the second one is negative 4 equals 2x minus 3. It's just that we as mathematicians, spoiler alert, we're lazy. We are incredibly lazy professionals. If we can get away with just making one symbol represent two things, we will certainly do it. So the entire reason plus or minus exists is because we were too lazy to write the same equation twice. So whenever you see a plus or minus, if you add 3 to the other side, that does not become a plus or minus 7. When you add that 3 to the other side, it is two equations. So I'm actually going to do this without looking at it as two equations. I'm going to treat it as one. When I add the 3 to the other side, that does not become plus or minus 7. That becomes 3 plus or minus 4. It stays that way. When I divide by 2, I don't divide the 2 into the 4. I divide everything by 2, and I write it. Kind of ran out of space, but that's fine. As x equals 3 plus or minus 4 all over 2. At this point, you can differentiate between the two answers. 3 plus 4 is 7. 7 divided by 2 is 7 over 2. 3 minus 4 is negative 1. Negative 1 divided by 2 is negative 1/2. And these are my two answers. But don't treat the plus or minus as if it's just thrown in and you forget about it. All right, let's move on to problem number 2. Again, I like this to be equal to 0. It's equal to negative x. I don't want that equal to negative x. I'm going to have to add the x to the other side. There we go. Now I can breathe a sigh of relief because it's equal to 0 equals negative 2x squared plus x. Then I'll put that plus 1 all the way out there on its lonesome, and I'm going to ignore it for a bit. Okay. Here's where we're going to face the two problems I was talking about earlier to y'all. First, the middle term is just x. It's 1x. Middle term is odd. That's going to be an issue. But the bigger issue is if you look at the number in front of the x squared, that's not a perfect square. That's not a 4 or a 9 or a 16, a 25, 36, yada, yada, yada. That's 2, which is not a perfect square, and it's negative. You can't have a number times itself that's equal to a negative. So we've got to navigate through that. You got two options. Division, multiplication. Division, fractions will show up, but the area model, at least in my opinion, is a little bit easier to do. Second, we do multiplication. It's easier to conceptually do, but the numbers get bigger. So make sure you have a calculator handy. It does not matter what you do. But our goal is to turn this into a perfect square. You can either divide everything by negative 2 or multiply everything by negative 2. I'm going to do the multiplication route. Take the entire equation and multiply it by -2. 0 times -2 is 0. -2 times -2 is 4. Then we'll get a -2x. And then we were going to get a -2. Now that leading term is a 4x squared. Now it's a perfect square. Now we can complete the square. Incomplete area model. 4x squared goes in the top left. That's going to be 2x times 2x. These two boxes need to combine together to get me a -2x. That's just -x and -x. So far, so good. But here's where you have to start thinking in fractions. You have to ask yourself, 2x times what number is equal to -x? It's -1/2. Meaning the part that we are missing is positive 1/4. So we're going to have to add a fourth here, and we're going to have to subtract a fourth here. Ugh, start writing that upside down. Those were the numbers we were missing. So this factors into 0 equals the quantity of 2x minus 1/2 quantity squared. This is the same thing as -8/4 minus 1/4. So that becomes a 9/4. See how this becomes more complicated. Fractions start showing up more regularly, specifically when the middle term is odd and the leading coefficient in front of the x squared is not a perfect square. If those two things happen, fractions will show up. This, believe it or not, is actually a problem that has relatively nice fractions. But then the rest of this technique is roughly the same. I'm actually going to have to go off to the left. I'm going to have to add the 9/4 to the other side. I actually designed this problem to be relatively nice. Didn't want to be too mean right off the get-go. I got to get rid of that square by square rooting both sides. The square root of 9 is 3. The square root of 4 is 2. I'm going through this really quickly because y'all have passed middle school. So I'm assuming y'all know this already. I'll go up here. It's going to be 1/2 plus or minus 3/2 equals 2x. I'm not going to do any major math in this next step. I just want you to realize 1/2 plus or minus 3/2 is the same thing as 1 plus or minus 3 all over 2. Multiply both sides by 1/2. Yes, I could divide it by 2, but I want to multiply by 1/2 because I don't want to introduce fractions inside of fractions. And that'll give me 1 plus or minus 3 all over 4 is equal to x. This is where we can get our two answers. 1 plus 3 is 4. 4 divided by 4 is 1. 1 minus 3 is -2. -2 divided by 4 is -1/2. These are my two answers. We are now done. This is the process of completing the square and then a combination of what we just got done doing, which is solving using square roots.